Swayam Prabha. Digital India. Educated India.
Hello dear students, in today's class we will try to understand what is the meaning of total derivative, and we will try to see how we can derive the continuity equation. So far we have understood to write the momentum equation or to account for various different types of forces and how we can add them together to get the equation of motion or to get the rate of change of velocity per unit mass. Right. Now, in today's class we will try to see what is called as a total derivative. We very well know what is a total derivative. Mathematically speaking, if you have done any course on differentiation or partial derivatives or stuff like that, you must have heard what is a total derivative. Now, here the context is slightly different. Different in the sense, when we talk about a derivative, what we are doing is we are trying to account the change, let us say, in a particular physical quantity, for example, temperature. It can be any quantity. We are trying to account the change in a physical quantity with respect to another coordinate, with respect to a coordinate actually, with respect to something that we can measure. Let us say if x is something that you can measure, you know how x will change from 0 to let us say 10, or you can also have t which can change from 0 to let us say another number 10. What will happen to a physical quantity which is temperature while x changes from 0 to 10? That is the basic idea of a derivative. How does it change? Whether it will increase, if this derivative is a positive quantity, it indicates that as x changes from one point to another point, the temperature will change. Let us take an example. Let us take, we consider this to be a cubical volume or a three-dimensional space. Now, if you have a measurement made of the temperature at this instant when x is equals to let us say 5. And when you say that, when you measure the temperature inside at every value, at every incremental value of x, and if you see that the temperature is increasing, or not directly saying the temperature is increasing, when you say that the temperature with respect to x is changing, it will indicate that whether it is increasing or decreasing. All this information is basically given in the form of a derivative. Right. Now, what happens is many times you may have to, while calculating the derivative, you may have to fix few other coordinates. Let us say if you are working in a three-dimensional space where you have x, y, z, and also let us say time, these coordinates are called as the independent coordinates. That means with respect to these coordinates you are defining something else. Any other coordinate, let us say pressure, volume, temperature, density, all these parameters, the quantities can be called as the dependent coordinates or the dependent variables. So, what do they depend on? They depend on the independent variables, independent coordinates. Right. Now, as far as the sometimes what may happen is if you want to calculate the change in a particular physical variable, you may require to keep some other physical variables or coordinates as a constant, and keeping them as a constant you calculate the change. Right. Now, the derivation or the formal definition of the total derivative is completely different. When we are talking about the total derivative in atmospheric physics or in the context of fluid dynamics, what we are trying to account is, let us say if atmospheric motion is to be understood, what will happen if this, let us say, if this volume of air moves from one point to another point. See, if there is a temperature T inside, okay, if this temperature is T inside, if this goes from one point to another point, what will happen to the temperature due to the motion itself, not because of the other physical quantities? What will be the effect of motion from one point to another point? This change is accounted in what is called as the total derivative. It is also called as, this total derivative is also known as the material derivative. It is also known as the substantial derivative. Substantial derivative. These three are the different names that we call this particular change. Now, when you talk about total derivative, it is even more important for us to understand what is air parcel. So, this description of air parcel may actually be repetitive. You may have heard about air parcel in some other part of this course. So, what is an air parcel? Air parcel is a infinitesimally small volume of air freely suspended in the atmosphere. So, air parcel is the entity over which we apply the laws of physics, and we try to understand how this air parcel will move from one point to another point. So, this imaginary entity in the atmosphere is called as an air parcel. Now, air parcel has a very distinct properties or characteristics. We always assume if the air parcel is existing let us say at a particular height, then we will assume that this air parcel will have the same level of pressure inside and outside. That means its pressure will be same as the pressure of the surroundings. If you push this air parcel to lower altitudes, or if you, let us say, if you displace it to higher altitudes, it will automatically adjust itself and making the pressure to be the same. And we also assume that the changes that happen inside the air parcel are also assumed to be adiabatic in nature. That means there is no exchange of heat or energy for that matter with the surroundings, but what is it that keeps constant is that the pressure will always be a constant. So, no matter where the air parcel is, its pressure will be always equal to the pressure of the ambience or the surroundings, right. So, this is the formal definition of an air parcel. So, air parcel is just a point in the fluid, just in the fluid continuum. Air parcel can be considered as a point, and this particular point is very well defined by the dynamical variables, let us say pressure, volume, temperature, density and so on. And we also assume that the field variables, let us say pressure, volume, temperature, density and so on, the field variables and their derivatives are assumed to be continuous functions of position and time. The field variables, so these are the field variables. Field variables are continuous functions of space and time. Space and time, right. Now, when we write various equations, we will try to write those equations pertaining to the air parcel, this point, right. Now, so far what we have done is we have by understanding the various different types of forces, we are able to write the rate of change of velocity per unit mass has been written as 1 by rho del p plus g star plus omega square r plus omega cross v plus nu, right. What this expression is tells you is we have seen what are the different forces that are appearing on the right hand side, and we have added all of them together to account for the rate of change of velocity per unit mass. This equation is called as the momentum equation, right. Now, something that is missing in this equation is is the simple fact that this equation is of course valid, but we should also account for changes which may occur due to the motion itself. Now we are trying to write equation of motion for a fluid. Now what will happen if the fluid is moving from one point to another point? How these forces will interplay? How will be the interplay between these forces? And will there be any function of the movement of fluid from one point to another point can be brought into these equations? Is actually the topic of discussion for this particular lecture. Right. Now we are trying to understand what is the basic objective of this particular, let's say, series of lectures. We are trying to understand how the movement happens in atmosphere. What are called as the atmospheric motions? How do they occur? What are the guiding factors? So atmospheric motions, let's say, they are not all of them don't really fall into the same category. That means all of them are not the same. They should not be treated equally. Let's say, for example, if you look at this equation, when I was just putting together this equation, I must have told that this equation should be sufficient to understand or to explain any type of motion in the atmosphere. It can be a very small scale motion up to a very large scale motion. Now, when you say that, if you are trying to understand the motion, it is very important to scale it. That means you put a number which is relevant for that particular type of motion. So, for example, if you take the scale sizes, if I indicate the scale sizes with lambda, for example, a tornado will be of the order of 10 to the power of 2 meters. A cloud, a cumulonimbus cloud, its size will be of the order of, let's say, 10 to the power of 3 meters. A hurricane, its scale size will be of the order of 10 to the power of 5 meters. You take a cyclone, its size would be of the order of 10 to the power of 6 meters. So, what all of this mean is that, so different types of motions have different scale sizes. So, that means in this equation not all the terms may be relevant for all these scales, may be relevant across the scales. So, we may have to choose which terms are reasonably higher on the magnitude side, or which terms are relevant or non-relevant, right. But the detail of understanding how different terms will appear or will vanish will be a topic for another lecture. But what we are trying to do now is we are trying to see how this derivative which appears on the left hand side is the rate of change of velocity with respect to time per unit mass. Will it be sufficient to account the motion of the atmosphere from one point to another point, right. So, that is the basic idea of the total derivative. So, for example, I will tell you how the total derivative can actually be understood. Okay, let us say, for example, you take an air parcel to be existing at the bottom of a hill. Now, that there is you measure the pressure inside the air parcel with P, right, at the bottom of this particular hill. You also measure the temperature, right. Now, when this air parcel goes from this point to this point, let us say if you write dP by dt, what are you trying to account? Let us say if this ascent has taken you 5 seconds. So, what you are doing is we are trying to account what will be the change in the pressure within a duration of 5 seconds. So, but what is missing in this is that in this approach what is missing is that there is an information of height, because let us say if pressure is P is equals to P naught exponential minus h by h. What it means is that the pressure changes exponentially as you go up. So, it means the pressure will decrease. Now, the missing factor is that if you only keep an account of the time but don't really look into what is happening to the air parcel, in which direction it is moving, in which spatial coordinate the air parcel's movement is recorded. If you don't pay attention to all that, you won't get the actual description, right. So, you must account the change across change that is following the motion. So, when you account for change in a physical quantity, change following the motion, change following the motion, this change, if you account for this change, that is represented by the total derivative. So, total derivative allows you to calculate change in a physical quantity, in a physical dynamical physical variable following the motion across its trajectory, right. So, dp by dt is sometimes not sufficient, right. Now, for example, let us take an example of temperature. Temperature is a function of position x, y, z and also the time. It starts from one point, it's after an interval of time, its position is something else. So, the temperature refers to a point of observation. Where is the point of observation? The point of observation is the air parcel, right. Now, let us say if the initial coordinates are x 0, y 0, z 0 and t, then there is an incremental displacement of delta x, delta y, delta z and delta t. So, the final set of coordinates would be x naught plus delta x, y naught plus delta y, z naught plus delta z, t plus delta t. Right. Now, so what is the change in temperature now? If the air parcel is moving from one point to another point, the change in temperature obviously has to depend on the x, y, z and t, right. So, if temperature is a function of all this, the change in temperature should as well be dependent on all these quantities. So, I will write delta t is equals to dou t over dou x into delta x plus dou t over dou y into delta y plus dou t over dou z into delta z plus dou t over dou t into delta t. So, what is this expression telling you? So, you are trying to find out or account the change in the temperature. Now, the change in temperature may have been due to change in temperature along x axis, change in temperature along y axis, change in temperature along z axis or change in temperature just as a function of time. Now, just if it is just as a function of time, you are not asking whether the air parcel has moved across x, y or z, and if this movement was able to influence the temperature in any way. Just to be sure, if there can be any temperature change that can be brought in across x axis, y axis and z axis, you have accounted for all the possible inclusion, right. Now, if I now divide this delta t over delta capital T over delta small t, then I will have to write dou t by dou x into delta x by delta t plus dou t by dou y to delta y by delta t plus dou t by dou z delta z by delta t times plus dou t over dou t. What is this? So, we have just divided the entire expression with respect to time. Right. Now, if we just say that when the limit delta t tends to 0, you can write delta t over delta small t is simply equal to dt over dt. So, which allows you to write dt over t. The rate of change of temperature with respect to time is equals to dou t over dou t plus dou t over dou x into u plus dou t over dou y into v plus dou t over dou z into w, because you have written delta x by delta t as u, delta y by delta t as v, delta z by delta t as w. So, you can write dt over dt is right. So, we can write this term as dt over dt plus right. So, the total rate of change of temperature with respect to time does not just depend on dou t over dou time, but in addition it also have another factor, right. So, totally the derivative is larger than what it should be with respect to just the time, because we have an additional factor, right. Now, this the first term that appears, what is this? This is change, this is of course change in temperature. This is change in temperature with respect to time. This is change with respect to only time. Change in temperature with respect to only time. The second factor that appears is generally called as the advection term. What is the meaning of this advection term? Advection term tells you what is the change because of the motion. That means because of, let us say, because of the air parcel has moved from one point to another point. Like for example, the example that I have taken was the hill. No, right. So, let us say if I say that it has taken me 10 minutes to transport the air parcel from from the bottom of the hill to the top of the hill. Now, if I account the change in pressure only with respect to the time, that will be the term number 1. If I also account with respect to position, because while it was doing so, what is the change because of the change of location from one point to another point following the motion, that would be the advection term, right. So, this is the basic difference. So, that means now you should not write when you are writing an equation of motion, and if you are trying to account the change with respect to change of a physical variable with respect to the coordinates, you should not write a simple derivative, rather you should write the total derivative. So, which means the equation of motion should now be written as, let us say, dv if v is the velocity. Now, it is very here it is this u vector is u I cap plus v j cap plus w k cap. Of course, this is implicit, but just for the sake of completeness I write plus right. So, this is the momentum equation. This is the momentum equation which is written with a total derivative. Right. Now, a direct consequence of understanding the momentum equation is what is this equation conserving as such is this is the conservation of momentum. Momentum is conserved, right. So, in this equation every term that you see is per unit mass, right. So, this is the consequence of the conservation of momentum. Now, most importantly, this equation, like the way it appears, is the most fundamental or the first governing equation that we call in atmospheric physics. What is it telling you? It is telling you how does the interplay between the forces affects the rate of change of velocity of the fluid parcel. So, what do you have on the left hand side? You have on the left hand side you have a velocity. Whose velocity it is? The velocity of an object. Now, if the atmosphere itself is a fluid and we are not talking about an object which is moving through this fluid, rather we are talking about the fluid itself. So, in order to quantify that particular fluid or in order to objectify that fluid, we take what is called as an air parcel, right. Now, I have described what are the basic properties or basic assumptions to consider an air parcel, but there are two different types of air parcel. One, a Eulerian air parcel or control volume. Air parcel is basically a control volume. What is the control volume? Over which you apply the laws of physics. Control volume or the Lagrangian control volume. So, Eulerian control volume is actually kind of fixed with respect to the frame of reference, but the Lagrangian control volume is something that moves from one point to another point. Now, what we can do is the subsequent conservation law that we should actually look into is the conservation of mass. Conservation of mass leads to what is called as the continuity equation. So, in this class we will take up one form of the continuity equation, and in the subsequent class we will see the second form of the continuity equation. So, continuity equation can be derived for both the different types of control volumes, which are the Lagrangian control volume and the Eulerian control volume. So, in this lecture we will try to see what is the Lagrangian control volume and how we can obtain the continuity equation. So, continuity equation is basically trying to see what is dm by dt. That means, how will the mass change with respect to time. So, if it remains a constant, you will say that the mass is conserved, right. So, the Lagrangian form of the continuity equation. So, here the control volume is a fixed mass of air with a mass delta m. So, delta m can be written as rho delta v or rho delta x delta y delta z. So, Lagrangian control volume is a tagged group of particles which moves with the fluid, which is moving along the fluid. Now, like I said, there is another type of control volume which is not moving, rather it is fixed with respect to this coordinates. What is moving? What is moving is the fluid itself. Now, the fluid is going in, coming out. So, the rate of change of mass dm by dt in this case should be the rate, or should be, if it is positive. So, inside the control volume, if the rate of change of mass is positive, that means there is lesser amount of fluid going out in comparison to the amount of fluid that is getting in. If it is negative, that means there is more amount of fluid that is going out in comparison to the mass that is coming in. So, in the second case, it will mean the presence of a source inside, or in the other case, it will mean the presence of a sink inside. Right. So, here the case is different. How is it different? Here the control volume is not fixed, rather it is moving along the fluid, right. So, we will for the conservation of mass, we will say that this delta m needs to be conserved. So, we will try to find out the rate of change of this particular mass. If it is following the motion, then we have to use the total derivative, nor the normal derivative. So, we will write rho delta v d by dt of rho delta v. So, we can write it as 1 by rho d rho by dt plus 1 by delta v d by dt of delta v is equals to 0. We would expect that mass remains conserved. So, that is why we have written that is equals to 0. But we can write this 1 by delta v d by dt of delta v as 1 by delta x d by dt of delta x plus 1 by delta y d by dy of delta y plus 1 by delta z d by dz of delta z. Now, since the control volume is moving with the velocity of the fluid, right. So, let us consider the fluid is existing at an initial point of ua, then it moves with a velocity ub, right. So, at the point a, the velocity u a is equals to dx over dt at a, and at b the velocity ub is equals to d by dt of x plus dt, right. So, the difference in the velocity, so the difference in the two speeds between ub and ua is delta u is equals to ub minus ua, which is d by dt of x plus delta x minus d by dt of x. So, we can write delta u is equals to d by dt of delta x. So, now coming back, 1 by delta v d by dt of delta v is dou u by dou x plus dou v by dou y and dou w by dou z, which is equals to del dot u. Now, bringing back the 1 by delta m d by dt of delta m is 1 by rho d rho by dt, substituting everything, plus 1 by delta v d by dt of delta v is equals to 0, which is 1 by rho right. So, 1 by rho d rho by dt plus del dot u is equals to 0, or we can write it in a familiar form that we can easily remember. The rate of change of density is equals to minus rho times del dot u. So, this is what is this? On the right hand side you have the divergence of velocity that is appearing. So, this is the equation of continuity. So, the rate of change of density is equal to the negative of the density multiplied by the divergence of velocity. So, this form of continuity equation is called as the velocity divergence form of the continuity equation, right. So, what we have learned in today's lecture is we have understood what is the need for a total derivative and what is the meaning of the advection term, and having seen that we have written the momentum equation using a total derivative. So, basically the total derivative is a derivative or is a process of accounting the change while following the motion, right. And using that we have seen what is a control volume or what is an air parcel, and we have derived the Lagrangian form of the continuity equation. So, what we will do in the next class is we will try to see the Eulerian form of the continuity equation, and we will also try to see how these two forms of continuity equations are basically identical to each other, right.